Gentlemen, please welcome Charles Torre.
Okay. Excellent. Thanks for showing up. It's great to be able to do Going Native again. Last year was awesome. Wonderful to see all you people, all you programmers in the audience. There's people online. Thanks to the Channel 9 team for streaming this live. Really appreciate that. So you can ask questions online, but we're going to take questions from people in the room. Priority, you came. That's excellent. We have a great 3 days for you today. We're going to stay pretty much ISO for day 1 and day 2, meaning we're going to focus mainly on standard C++, with some VC++. Day 3, we're going to kind of interleave some Windows and some more VC++ with ISO. It's going to be excellent. But without further ado, I'd like to introduce our keynote speaker. It's so wonderful to have Bjarne Stroustrup here, the creator of C++. He's going to teach us a little bit about its essence. Thanks for coming. Actually, you have your mic.
Okay, yeah, welcome. Seems that the mic's working. So, in the next couple of days, you're going to hear a lot about the latest and greatest in C++. You're going to hear a lot about advanced techniques and new features. And I decided that in a keynote, I couldn't go too much into that. So I'm going to trying to do the opposite. I'm going to try and focus on what is the essence of C++. What is it that's been constant over the decades? And basically, what is it that's kept C++ alive and kicking? Of course, I can't quite resist showing some new and nice stuff. So the last 15 minutes or so will be about something from C++ 14. But basically, I'll talk about aims and constraints on the development first. Then I'm going to try and explain C++ in 4 slides. And then go into some details about resource management, object-oriented programming, generic programming, and what challenges lie ahead. So basically, what is it we want out of a programming language that is aimed, among other things, for systems programming? We want type safety. That would be ideal. We can't be perfect about that with the need to deal closely with hardware and with the C inheritance. But it's an ideal. It's something we aim to improve. We want resource safety. That is not just memory. So I'm going to argue that we really don't want to leak anything, and things can be things like locks and file handles and stuff, not just memory. I'm going to talk about performance because, well, that is important. If it isn't important to you, there might be better languages for you to do. Predictability is very important for a large component of the C++ world, dealing with hardware, dealing with things that has to happen quickly or reliably and repeatedly. And we want a language that can be taught. We want something that is no more complex than it needs to be for the task it's doing. And of course, we want to be able to read what we're doing. You can write unreadable code in any language, of course. But we want to be able to write something on a good day that people say, wow, this is really nice and clean and clear. These are the aims. We're much better at it today than we were 20 years ago, and we'll be actually much better next year when we get C++ 14. And we want the primary concerns of mine is systems programming, embedded systems, resource constraint systems, and large systems. That is sort of strictly the domain of hardcore professional programmers. And it may very well mean that if you have a tool for that, it's good for a lot of other things. And that was one of my surprises early on, was that so many systems has a core to it where what I'm most interested in is essential. And then C++ is so general that it will do the rest also. So C++ is expert friendly, definitely. And the problem is that that's not enough. if it's only expert-friendly, if it's just expert-friendly, there's nothing for novices. So we must evolve the language into something that's a bit more friendly to novices without giving an inch or byte or a cycle for the experts who really needs the bytes and the cycles. So part of this is my answer to what is C++. I have my ideas. They're not necessarily the same as anybody else's. They're probably a bit broader than what you hear in most places. That is, I try to see the whole elephant, and I find that in forums on the web and conferences and such, people play blind man and the elephant, and they are absolutely certain that their part of the elephant is the whole beast. They're wrong. So this is my summary of C++. If you have to do it on one slide, it's a language that provides lightweight abstraction facilities, and its key strength is in areas where you build software infrastructure and where you have resource constraint applications. It's not the elephant that's lightweight, it's the abstractions you can build. That is, anybody can build a really slow big abstraction. But building a point or a coordinate or a complex number that you can afford in competition with languages that have built-in facilities like that is hard, and that's where C++'s strength is. C++ is comes from two of the main lines of development of programming languages. There's the lower line here where it's basically exploit the hardware. You start with assembler. We went through BCPL and C, and C++ gets a lot of its low-level stuff from C. You can see the people there. That's, of course, Dennis Ritchie. That's David Wheeler, who was my thesis advisor and one of the 10 people who can claim to have written the first compiler. He can also claim to have written the first program ever running on a stored program computer. So this is a good thing, a good long tradition. Exploit the hardware maximally. On the other hand, the biggest improvement in programming languages ever was done by Baggers and his team at IBM when they decided to improve productivity of programmers by letting programmers write in a language that was fit for humans instead of this load and store hardware close stuff. So they got Fortran, and you could get programs written in exactly your own language, provided you were a certain kind of engineer and certain kind of scientist. So that's how we got Fortran. And as soon as this idea was had, everybody wanted a language from their particular domain. So the business people got COBOL, where you could say business-like things, copy files, write to tape, and things like that. And very soon there was a couple of hundred of these languages, and it was a terrible mess because every language was good at one thing. It spoke one language of one subset of the computing community. And so the brilliant idea here from Christian Nygaard was to generalize this, saying, okay, if you have a concept, if you have an idea in your head, on your blackboard, or whatever, you should be able to put it into the language in general. So instead of building languages around special purpose concepts, you provide the facility for building new things. They called it classes and class hierarchies. And so here comes the line of general purpose abstraction from the hardware, and I borrowed that and got the initial C++. And we've been developing that ever since. And there's been other developments in the world, of course, but I'm talking about this line here. So what we need is to be able to do things really well close to the hardware, as well as anybody, and provide general purpose abstraction so that we can actually get the concepts we need in our programs, as opposed to always talking about bits and bytes. So C++ is of course not perfect. Anybody who claims to have a perfect language is either a salesman or a fool or both. And C++ doesn't actually aim to do everything for everybody. There are things that are less interesting and things that you just don't need, say the efficiency of the close to hardware things, or you don't need the abstraction. So there are alternatives. We're not trying to be everything for everybody. It has a solid fundamental model, despite of what you might have heard or what your professors might have taught you in class. There's a quite solid model for what C++ is, and I'll try and convince you about that. But basically it has C's model of the hardware, and it has facilities for principled added new concepts to a program. And then this has been refined for 30 plus years. That is, it works. This also means that it has a lot of warts. It also means that we know the warts. People very often choose something new because, well, they haven't learned its weaknesses yet, so it looks perfect. We know the problems with C++. That's partly an advantage. Long-term stability is a feature. That is, in the depths of all this compatibility stuff and crud, you find that it is really nice that my programs from 10 years ago still runs. It's really nice because it sort of assures us that our programs will run in 10 years. Again, we're trying not to break old code, and performance, we want to be a match for everything, and usually we are. This leads to a set of interesting applications, for instance, that are very widely used. It actually, what C++ offers clearly pays off for somebody, otherwise they wouldn't be using it. So I'm going to go into this in a little bit detail. I'm going to try and get C++ down to just 4 slides. And the rest is details. So if you understand int and vector, you'll understand C++, and there are a lot of details, but don't get lost in them. That's the point. By the way, I've just written another book. It's very thin, 180 pages of stuff, plus an index, which claim to present all of C++ at a certain level of detail. So if you actually are an experienced programmer, here's where you can get an idea of C++. So that's the end of the advertising for now. So what do we do with C++? First of all, we have to map things to the hardware. The hardware is where programs run. They don't run in mathematical abstractions, they run on hardware. And basically, the primitive operations are the instructions on the machine, and we have built-in, we have value types. Many of them map straight into the hardware. Some don't, but they're very simple. They're values. If you understand an integer, you understand about anything that's a value. You can copy an integer, and you can do things to it. The other kinds are handles. They have a handle that controls access to some other data that controls the values. So here, for instance, you have a vector that keeps track on how many elements there are, and gives you a subscript operation and copy operations and things like that to manipulate the value. And there's a lot of things like that. But those are the 2 fundamental building blocks we've got, and we can compose them by simple concatenation. That's what happens in arrays. You put objects next to each other, and classes structure, well, you put them next to each other, usually considered in a different dimension, but basically there's nothing more to it. There are ways of composing these basic things, and when you look at your code, you can sort of think about what is in the memory and understand it, and when it comes down to the primitive operations, you can see which primitive operations are done. Then, to get away from this very concrete low-level view, we have classes. And the most important part of classes, I think, actually is constructors and destructors. We define ourselves a new type, and we initialize it with some value. That's called a construction. and when we are finished, clean up the mess. So if this is a resource handle, this will acquire resources, and this one will release it. So basically, here's a quote from about 2 weeks into the design of CV classes a long time ago. A constructor establishes the environment for the members to run in. The destructor reverses its actions. Slightly paraphrased because I hadn't invented the words constructor and destructor yet. But that's where a lot of C++ comes from, right there. And now, once we've got classes, eventually we get abstract classes and inheritance. Here's the way we define an interface that completely insulates the users from the implementation and vice versa. It has a couple of virtual functions that are pure virtual functions. There's no data member, so it's not a brittle-based class. You may have to manipulate these things through pointers and references. At least that's what essentially everybody does. And that implies some overhead, and it implies some lifetime management that can be very messy if you don't think it through, and you can build these hierarchies based on it. Next, we have parameterized types and classes using templates. That's the essential support for generic programming. And secondarily, it allows compile time computation. Basically, you can have a vector that's parameterized by its element type. You can have a sort function that's parameterized by its container type. And so we can make a vector of doubles like that. And we can sort some vector with that. That's the essence of generic programming as represented in C++ and supported. So there are some things that is not C++. As I said, it's not everything. And some of the things that are really quite fundamental in the design of C++ for good and bad is there's no crucial dependence on a garbage collector. A garbage collector is a centralized resource, so there's contention for it in a machine. I remember the big old Sun machines, 64 processors, real beast, and what do? 63 of them sit waiting for the garbage collector. So C++ was designed not to have this problem, and it has other problems in exchange, but this is a fundamental decision. Similarly, there's no guaranteed type safety. We did not want it for all constructs. We needed C compatibility. We have history. There are needs to deal with hardware that requires breaking the type system. We would like to minimize it. We would like to encapsulate it. But there was a decision a long time ago that C++ runs on the real machine. It's not a mathematical abstraction that it runs on. And there's no virtual machines. If you want to run on a virtual machine, you can. But something has to run on the real machine, on the real hardware. For instance, the implementation of a virtual machine. And also there are many domains in which you cannot afford a virtual machine and you want to exploit facilities of the hardware. If you're running in a virtual machine, exploiting a GPU gets rather tricky. If you are on the machine itself, you can go into something that might be type unsafe and it might be an extension, but you can get there. I have a few pictures on these slides. They tend to have something to do with C++, so you can wonder what it is. That there is a distributed computing system with wheels. There are also things that are not C++ for reasons that are regrettable, but they're market realities. There's no huge standard library because we don't have an owner, we don't have a sugar daddy that can produce free libraries to ensure market share. We would like to fix that. I'm sure Herb will say something about it. Yeah, he's got a big grin on. It's one of his favorite topics. And we'd have no central authorities to approve, reject, or help integration of libraries. Integration of libraries is very difficult. And we'd like to do much better than this. But for the moment, these are the market realities. This is the way the world has been for C++ all the time. And so we have no standard graphics and GUI. We have sort of maybe 25 competing frameworks, which is just as bad as none, roughly. Again, it's unfortunate. And we don't have all of these things here standard. They exist. You can pick them up. You can use them today. But they are not standard, and we would like to do better than that. I don't know if you remember the dragon book, the knight is slaying the dragon of complexity or something like that. Well, sometimes the dragon wins. Okay, so going to start on slightly more technical things. We're going to look at resource management. Basically, we have things that we would like to control in the system, like memory, the elements of a vector, the characters of a string, the file handles that the operating system provides, threads, locks, and things like that. And basically, what we want to do is to have a handle that we use to control access and make it convenient to use these things. And basically it uses, the standard way of using this is it uses the constructor and destructor. The constructor acquires the resource, here it's memory because this is a vector, and the destructor, well, gives the memory back again. So it's very simple. Here we have a function that has a vector, it makes a vector, and at the end, whenever we leave this function, however we leave it, the destructor cleans up by releasing the memory again. And the basic idea is very, very simple. The details can be quite hairy, depending on the resource, depending on the constraints of the problem and such. But keep that picture in mind, and you can write a lot of good code. The handle is usually scoped. As long as the handle is in a scope and not put on the free store itself, unless held by a handle, cleanup is automatic and simple, and the resource is held for a minimal amount of time, namely the scope in which it was created. And basically this is sort of the code here. What does a constructor do? It requires a resource, sets the memories, initializes the memories needed to control things, and possibly does some initialization over in the resource it has acquired, and the destructor reverses that. Very simple. So a resource is anything you acquire and have to release explicitly or implicitly. That's my definition of a resource. And a resource should have an owner. I really dislike stuff that just floats around in the system, and well, people hope somebody will take care of them at some point. If there's an owner, the owner's job is to make sure that the lifetime is managed, that it's initialized properly, that it's cleaned up properly. And the ultimate root of a resource is a scoped handle. It doesn't have to be scoped, but it's much easier if you keep it in a scope. This is often known as resource acquisition initialization. Horrible mouthful, often reduced to RAII. I can say it's a horrible mouthful because I invented it and I named it. I should have named it something better, but well, hindsight is relatively easy. And basically, if you fail to acquire your resource, you throw an exception. It's one of the fundamental reasons there's exceptions in C++. It is there has to be a way of getting out of a task that you've been asked to do and can't do. Like a constructor that can't construct its object has to be able to get out of there. If you don't have exceptions, you have to fake them. You try to construct an object and the object is set in a bad state and you have to test the valid bit or something like that. Pretty horrible stuff. And basically the rules for not leaking becomes never throw while holding a resource that's not owned by a handle. So if you do something silly like acquire some memory and just hold it, a pointer to it, and then throw an exception, you're in deep trouble. We'll get back to that. Okay, so here's an example. We have a mutex. It's a system resource, and we have something we want to share, which is the shared data here. and we want to control it by a mutex. A mutex is a system resource, and it is represented in the standard library by the mutex class. And the mutex class actually is a handle to the system resource. And so, system resource, yeah. Just think about it as a system resource. We go into a scope, we take a lock on it. That is the local object that holds the mutex, use the data, and then we get out of there. And we don't care how we get out of there. Now, this is, of course, overly simplified. We often have more code working in a critical region than just there. So we can get out of there by returning, by falling off the end of the scope, or by throwing an exception. But in all of these cases, the lock guard will release the resource. That's the main point. Acquire, use, and release. So here's an example of what code I find when I look around that I think is pretty awful. It's not just written by Java programmers, but it's actually getting more common than it used to be. There's always been people writing code like on the screen here, but unfortunately this is an increasing problem. So I get a gadget, I get it on the free store, I've learned object-oriented programming, everything has to be off in the free store and manipulated through pointers, so that's what I'm doing. Then I go down, I may throw an exception, and somebody might say, well, exceptions are bad because I just might have leaked a gadget. No, I'm saying you did something else wrong because you can get the same problem just from returning. In other words, I have this gadget here that I've acquired and I have to delete it, and somehow that puts major constraints on what I can write in this function. In particular, I mustn't leave without deleting P. And people then say they want a garbage collector, but you know, I didn't tell you what was inside the gadget. If that's just memory, a garbage collector will help you. If it's a file handle, a socket, and a lock, the garbage collector will not help you. So this code is bad. If I throw here, I have leaked a gadget and the gadget holds a lot of things. Well, so naked pointers are bad because they're hard to manage. So people say, let's use a shared pointer. A shared pointer is one of these handles and it holds a pointer. And when you acquire a pointer, it holds it, and if you get out of this scope, the shared pointer will release the resource if it is the last one that holds it. In other words, a shared pointer is a form of garbage collection. If I have a shared pointer, I can give you a copy and I can give you a copy, and the last one of us that gives up their copy will destroy the object. That's the idea of a shared pointer. But you know, I'm not actually sharing anything with anybody here. That gadget is mine, all mine. And so why am I dealing with garbage collection here? Even the shared pointer version garbage collection. If people think I'm misusing the word garbage collection, remember that originally garbage collection was defined by shared pointers, counted pointers. And there are languages that call themselves garbage collected because everything is a shared pointer. So this is a form of garbage collection. But you know, the use count for that gadget goes from 0 to 1, and eventually it goes from 1 to 0. That's all it does. I'm not sharing anything. There is in the standard library a unique pointer that will allow me to say, just hold on to this one. Destroy it if I leave the scope, when I leave the scope. And that's all. That's unique pointer. Don't share it with anybody. That's fine. But you know, why am I dealing with pointers here? Actually, the code I would like to be common and colloquial is like this. I make a gadget. What should a gadget be? The gadget should be a nice thing. If it holds something, it'll be the handle for what it holds. If it has a file handle in it, the constructor will initialize that file handle, the destructor will close the file again. If it has a lock, it'll do locks and unlocks as needed. If it owns memory, it'll acquire the memory and release it in the destructor. All of this is automatic. It's the gadget's job to maintain the gadget's resources, right? I mean, I have an abstraction, it should be a proper abstraction. So this is no longer a problem because the destructor for the gadget will take care of it. And so things are simple. I really like it when you take some complicated code like that and improve it by making it much smaller and simpler. That's the idea. We want to have simple things simple. There are things we cannot do with just the RAII model and such, and there's complicated data structures that require more thought. There are places where you require shared pointers, etc., etc. But simple things should be simple, and this is an example of it. So what do we actually use pointers for? If I'm saying pointers should not represent ownership. Handles represent ownership, and pointers live inside handles and are used by that. Also, so we reference resources inside a handle. You represent positions. So that's where we have pointers into arrays, like we use indices, and we have iterators and all of this good stuff, which are pointers in disguise, by and large. Represent positions, and we have to be careful. We can be careful, or we can have range checking. They're really good to passing large amount of data around, usually in the form of a reference or a const reference. That's how we get, say, two matrices into an add function. For matrices, we just pass const references. Pointers in various guises are really good at passing things to others. And people use pointers to pass things out of functions, results. And I'm going to show an alternative to that and motivate it. So here's the problem. We can get information represented inside a function. We can get information into a function, but how do we get it out again? And the idea of getting things out of a function, usually if it's a lot of data, if it's a complicated object, we put it on the free store and return a pointer to the stuff we put on the free store. And the problem is we've used new to get things on the free store, so who deletes? Is it the operation that created the objects, or is it the code that called that object? Neither of those solutions are ideal. Neither of those solutions are unmanageable, but a lot of the unmanageable resource management using a lot of pointers has its root in this problem. People don't decide who owns what and who's supposed to clean up what. So things pass through an interface and disappear. We can try and solve it by references. That's even worse, because if I return a reference to something that's on the free store, somebody still has to delete the pointer, and the obvious question is, what pointer? I don't see any pointer. A reference looks, when used, just like an object, and you have disguised the problem rather than solved it. We can pass a target object. So instead of adding two matrices and returning a result, we can say add a comma b comma c. It takes a plus b and puts the result in wherever c points to. That's a popular way of doing it. And the problem is that we're regressing towards assembly code. And output parameters is a well-known source of complexity and confusion. And when I say plus a comma b comma c, what does that mean? I have to read the documentation. At least we have got consts so that we can tell which ones were supposed to be inputs and which ones were not. But if people are not consistent, or if they just look at the code, what's what? This is a source of bugs. Similarly, the code that beforehand just looked like A becomes B plus C now looks declare some result type C and then plus A comma B comma C. That sometimes it doubles the amount of code you have to write. So I don't like that solution. It works. It's sometimes the best we can do, but we are regressing. We are throwing away a few hundred years of progress in notation. And we can return an object, and when we try that, that works nice. If the object I'm returning is an integer or a complex number, it's not a problem. If it is a matrix of 1,000,000 elements, even a modern processor can feel the pain. And so copies can be expensive, and then we start inventing tricks for returning objects cheaply. Well, that sort of works in the hand of a competent programmer in a code base strictly controlled by somebody who knows where doing it works. But in this area here is where we find a lot of the awful code that for not solving this problem permeates a 1,000,000 line code base and becomes sources of problems. So we can return a handle that's simple and cheap. Don't return the elements of the matrix, don't in terms a pointer to the elements, return the matrix, which is the handle. Okay, so how do we do this? Here, this is the way I want the code to work. I want a matrix that takes plus operation that takes 2 inputs and produces a result. And I want to do that by making a local variable. I want to fill it up with the good stuff I want to get out, and I want to return it, and I want to write my code like this. And this works nicely. In here R is a handle to all the elements, and the return operation is simply take that pointer there and give it to res, and then put a null pointer in its place. That's known as a move operation. Even little kids can understand this. Look, here's an object, right? I moved it over here. It's not here. Okay, only a computer scientist would make a copy, move the copy over here and destroy the original. You actually need a degree to figure that one out. Little kids at about age 6 months can do this. Okay, so what does it look like in code? There's this funny notation that says that this one is a move constructor. A move constructor is called from something that we don't need anymore, like the source of a return statement. And it does exactly this, as I said. Here it copies the representation and then zeroes out the representation. Now, it copies because that's what hardware does well for small things like a pointer or an integer. In the matrix example, it's probably just an integer. It may be a pointer, and it may be a pointer and a couple of dimensions or something. It's small. So this operation here, the move operation, is something that is really cheap. So if you want to move a 1,000,000 element matrix out of a function, it costs you 2 word assignments. That's affordable. Okay, so basically this leads me to the conclusion that no garbage collection is needed for this. Simple, implicit and efficient resource management, we can do that. And so we have a set of techniques. First, we store data in containers, and they should reflect the fundamental abstraction in the interface, and it handles lifetime management. And you handle all resources within a resource handle, not just memory. This is important. I don't want to leak sockets. I don't want to leak file handles, etc., etc. Your systems have a lot of resources, some of which I've never heard of. They're just something that in your system has to be acquired and released. That's a resource. All of those has to be managed. If you can't get this working, you can start using smart pointers. Unique pointers are very good at holding onto things in scopes. They're also very good to handle unique ownership, hand unique ownership over to somebody else. Shared pointers is for the cases where you can't work out the ownership. It's really uncertain who is the last user. Try not to get there, but when you get there, smart pointers, shared pointers will do the job. And finally, if you have gotten yourself into a mess, which a lot of us has, especially with old code, lots of pointers, no real understanding of who owns what, no really clearly articulated or a set of rules for error handling and resource management. This is not uncommon. Or if there is some clearly articulated rules, they may not be followed. In that case, we can plug in a garbage collector. And we get what's known as litter collection. There shouldn't be much garbage because we've already dealt with most of it there. So it's relatively cheap. C++ 11 specifies an interface for this. It can still read non-memory resources, but it can be efficient and you can effective, and you can go and do it if you want to. But the point is, the usual order of preference has been reversed here. It is not that the ideal is garbage collection, and then if we don't have garbage collection, we will do something else. No, the idea is perfect resource safety with minimal overheads, minimal resource retention times, and then eventually, if everything else fails, we can plug in a garbage collector. At this point, garbage collection becomes cheap. So, I sort of feel uncomfortable when I don't show code for a while. So let me show just a little bit some of the facilities that we have in C++ 11 with the general purpose of making simple things simple. So here I want to find all v's in C. And C is supposed to be a container, v is supposed to be a value that might be in the container. And how do I want to return that? I want to return a vector of pointers to the elements in there. So I know where all the pointers is. So basically I'm gathering the addresses, the pointers to all the elements that have value v in a container. That's fine. That's what I want to do. And I implement it by taking a local variable and I fill it up. I use the new for loop, the range for loop, and I said for all x's in C, and x of course is of the type of the elements in C. The compiler knows that, so I don't have to tell it. That's what auto says. And it's references because I wanted to collect information of where they were. If x equals to v, puts its pointer to it onto res, and when we're finished, we return res. So this is like that matrix example. Basically, I just make a collection of things, and then I pass it by value, return it by value. And vector is C++ 11 vector. It has a move constructor, so this is actually efficient code. Don't try this on C++ 98 because this will be a performance bug, but all the rest of here you can't write in C++ 11, so you're safe from that problem. And then we use it. We'll take a string. A string is a container of characters, right? And then I say find all p's in, for all p's in the result of find all. So I'm just going over that result, which happens to be a vector of pointers. And if it doesn't point to an A, we have something serious here, because I'm saying the A, and so there's a bug in string related. There's a bug in string, there's a bug in find all or something like that. This should never happen. But so this is fairly simple, and it uses a fair number of new features just to wake those of you up who hasn't seen this before. Let me just point out that auto is the oldest C++ 11 feature. I implemented it in 1983-84, somewhere in the winter there, and was forced to take it out for compatibility reasons. But it is actually notationally a very nice thing. I don't have to remember what the return type of find all is and what is the value type of that container that came in somewhere. The compiler knows, so I don't have to tell it. For generic code, that's really nice. Okay, so basically what I've been saying here about resource management and move semantics is deep into the standard. All the standard containers are handles, vector, list, syncly linked list, called forward list, etc., etc. And all the other standard resources like threads and logs and files and unique pointers use this kind of strategy. So you don't have to start from scratch writing this kind of stuff. It's already in the standard library, and you are probably already using it. If you are sorting a vector, you're already using some things like the move. Okay, now no presentation of sort of the essence of C++ could fail to mention object-oriented programming. But you know, these days I find just about everybody knows most of what there is to say, so I'm going to keep it very brief. C++ has a protection model for this. You have public, protected, and private stuff. I like stuff to be private because that limits the number of pieces of code and the number of programmers that can mess it up. If you have to use protected, there's no universal base class because I consider a universal base class an implementation-oriented artifact. There simply is nothing that is common to all types in terms of representation or interface. If you say that there has to be, you are imposing a time and space overhead. It might be the right thing for a limited domain stuff and may be very useful, but it's not fundamental. And a universal base class easily get to become overly general because that is really where you put things that are common for everything, and so you get more and more, and it gets harder and harder to maintain. There's multiple inheritance. This is considered controversial in places, but everybody who has static typing in any form has multiple inheritance of interfaces. And so I consider that non-controversial. And so abstract classes provides the most stable interfaces and the best separation between interface users and implementers. So we need multiple inheritance for that. Sometimes it's also useful for data. There's some minimal runtime type identification. So basically, you use inheritance when the domain concepts are hierarchical. So basically, you have to think not in terms of programming language things about whether to use inheritance. You have to think in terms of the problem you're trying to solve, the information you're trying to represent. And if you have a genuine hierarchical system, my usual example and the oldest ones are vehicles. A truck is a kind of a car, is a kind of a vehicle, and that kind of stuff. You use it. And it's very powerful. However, it has been seriously overused. There are people who think building a deep hierarchy equals good programming. And no. If your domain is a deep hierarchy, representing it with inheritance is just right. If your domain is a shallow hierarchy, maybe what you need is what looks like just an interface to implementations. And maybe there is no inheritance necessary, in which case you probably don't need a virtual function, you don't need any hierarchies. So don't overdo it. Think before you make things a member. So let's get to generic programming. This is the area that has seen the most progress and evolution over the many years, and there's something to say here. Basically, in 1980, I wrote the first paper on Siebel classes, the first paper on here, and it had a vector in it, and it was parameterized with its element type, and there are a statement there that macros will do the job. I was wrong about that. Boy, was I wrong about that. On the other hand, I had the right problem. I wanted generic programming. I wanted my vector to be parameterized on the element type, and I want my sort function to work independently of which element type it was. So in 1987, thereabouts, I wrote out the aims and designed If it only can do what I can imagine, there's just something wrong, because my imagination is not equal to the needs of even a room full of people like this, let alone all the programmers there are. There has to be zero overhead. And the reason was that my least favorite data type in C and C++ is the array. An array in C is a data type that's so stupid that it doesn't even know how many elements it's got. And that's a source for a lot of problems. It also converts in strange ways. It's a problematic. So I would like to have a vector or a matrix that would be a useful replacement for arrays in most cases. And the C and parts of the C++ community is obsessed with performance. So basically the zero overhead comes in here, not a byte, not a cycle. So we had to be able to do that. You have to remember that most people who think about abstraction and generic code thinks about indirect function calls. And you can't go through a jump table and still have performance comparable with manipulating arrays. Imagine if your operation for subscripting or your operation for going 2 elements over in an array was a virtual function call. You're dead in the water compared to arrays, and arrays would live on forever. So, and also, of course, I wanted well-specified interfaces like everybody else. I knew that a well-specified interface is the foundation of a lot of good architectural stuff. I was the one who put function argument checking and conversion into C++. What later in C became function prototypes and such. It's one of the first things I did. I knew the value of that. On the other hand, you know I didn't make it. 2 out of 3 ain't bad. Got the first 2. But the third failed miserably. It has kept me concerned, worried, and working on it for 20 years. And I'm going to finish this talk showing where the current state of that work is. But basically, I don't think I had a choice back in '87. I don't think anybody knew how to get all 3 simultaneously. And if you have to pick only 2, I made my choice. For C++, it was probably the right thing. So what we have templates, they do compile time doc typing. Basically, they expand the code, and then it checks the expanded code. And that leads to template metaprogramming. It leads to very good weaving of information from different sources. But it also means that an error is found in the generated code, in the instantiated code. And most of you will have seen the error messages you can get out of that. I used to think that sooner or later the compiler writers would get smart enough to write decent error messages, but I was not, well, it hasn't happened. I still get error messages that doesn't fit on my Linux window. They scroll off the top of the buffer so I never see the top ones, things like that. Okay, we need to do something about that. But let's see. Templates was a massive success in '98. It was better in 11 and it will be better still in 14. Basically, we have containers, we have algorithms. They're in the standard library organized as the STL, which stands for STL. And there's much more. So we need better support for compile time programming because template metaprogramming gets too complicated often. constexpr provides a facility in C++ 11 to generalize constant expressions. Basically, you can define functions that are to be evaluated at compile time. You can force compile time evaluation in places, and you can even do constant expression evaluation at compile time for user-defined types, provided the user-defined types are simple enough, known as literal types. I know some of the talks here at this will get into some of that. Okay, we are making progress. Basically, what we have now and what we're looking for is algorithms. We must get away from writing all of our code from scratch in the basic language. We need to raise our level of abstraction to the point where instead of everything being just integer adds and subtracts and things like that, we say we use this algorithm, like out of a catalog of algorithms. And here's sort of the classical example. We sort a vector and we find an element in a vector. The STL works on sequences of things, so you have to have the beginning and the end. But basically, this is parameterized. It is generic over the kind of container we are dealing with. Here's a vector, here's a list. And it's generic over the elements of those containers. And there's, I think, about 100 algorithms now that's standard. And I would hope you're writing your own and adding to it. We don't see as much of that as we should. Basically, we want simple and efficient and general implementations. Here we've got find. If you like C syntax, this is beautiful. If you don't, that's what you've got anyway. And we also want to parameterize with operations. That is, we parameterize over the container, we parameterize over the element type, and we parameterize over the actions to be taken. Here is a predicate passed to find if. I want to find anything that meets the predicate less than Griffin. And so we generalize find if that I showed before. It simply uses the predicate while we haven't reached the end and we didn't find the predicate, go to the next one and try again. If once you finish, you return. Okay, this has been in C++ in various ways since the late 80s, early 90s. So we write a lot of function objects. That's the way we represent operations, predicates, etc. They can carry state. That's important. They're easily inlined. They actually work better in simple cases than an indirect function call. And so here, less than for strings is supposed to take a string you're comparing it to and then compare when you ask it. And that's how it was done here. I take the Griffin, that's what I want to compare to, and whenever I want a comparison, it calls this object. If we get tired of writing these function objects, we can use lambdas instead, which is basically a notation that says, give me a function object and use it right here. So here I want to do the find if, and I want to compare the value with Griffin. Done. If you get tired of writing all of these begin ends, you don't have to. You can simply define your own versions that works over a container. It's not perfectly as general as using the pairs of iterators. It is notationally much nicer. So here's the find if. Find if in the container V, look for things that are odd. Okay. Back to the problem of specifying interfaces. I think doc typing is insufficient. It gives all of those bad error messages in addition to whatever good it does. It leaves error detection too late, and it gives compiler writers too hard a job because there are no proper interfaces. There's no way that says this is what this algorithm requires of its argument. It is not set somewhere. There's nowhere to say it in C++ 11. That also encourages people to look at the implementation details because they will look at them anyway. There's no interface that protects them from the details. And that means that every time you change the implementation of an algorithm, some user might be affected in a surprising way. So the user's interested what's inside those abstractions. They're not that abstract. And that leads people to start generalizing their implementations so that users, they have a greater user base. This gets into a mess sometimes. And furthermore, it doesn't integrate too well with other parts of the language. You have to teach this kind of coding in a different way than other kinds of coding, and you have to think about it in a different way, and that's not good. We're not very good at keeping one style here and one style there. It should be better integrated. So I think we have to rethink generic code so that it becomes similar to the way we think about other code. And we need interfaces to get better error messages, better specification of our algorithms. So here's what I like. Here's some traditional code. We have a square root of double, returns a double. We have a double, we call the square root of double with a double. Everything is fine. That's what we learned in some version or other on day one of our programming class. And if we give square root something that isn't a double, in this case a pointer to a double, we get an error. At compile time, right there, simple, straightforward. We all understood that very simply. Now I want to see the same thing with generic code. Here's a sort that sorts containers. Here's a container. Fine. We sort the container. Here we're trying to sort something that's not a container, because in this case it's a pointer to a container, and we should get an error. And we should get an error right here, and it should be comprehensible. So I would like to see generic programming as very similar to ordinary programming. So this is what we're working with in something called Concepts Light. It was known as constraints, but after people have been talking about concepts for a decade, invariably they became concepts. But since they're about less than a tenth of the complexity of the old C++ OX concepts, it became concept light. Sorry to Coca-Cola or whatever. So basically we're trying to answer the question, how do we specify requirements on a template document? And we want to state the intent. And we want point of use checking. So we're basically providing a set of functions that states what we are requiring of an algorithm. So if I have an algorithm that sorts, it'll ask for a container. If I have an algorithm that a container, if I have a thing that takes square root, it'll ask for a double or possibly a number. And this it's voted in as a C++ 14 technical report, technical specification, I believe is the technical term. It's designed by me, Gabby Das Reyes, and Andrew Sutton. Andrew Sutton has an implementation of all the basic stuff and most of the details. And basically, for those of you who have lived through the horrors of the C++ OX concepts, there are no concept maps, there are no new syntax, and there's no scope and lookup issues. The specification is very much simpler. So the first thing we had to ask ourselves when working on this is, what is a concept? And one of the notions that we came up with was concepts are fundamental. People were writing specifications that were very, very detailed and fiddly. There literally was 120 concepts in the C++ standard library. And look at it. How many concepts are there in algebra? A dozen? Is the C++ standard library 10 times as complicated as algebra? I hope not. Certainly it does not have 10 times as many fundamental concepts. So we have to concentrate on building concepts in the language as what you have that are fundamental to an application area. We also have to remember that concept comes in clusters that describes an area. You don't have a free choice really. If you are dealing with arithmetic, you can't define what it means to subtract independently of what it means to define addition. You cannot define multiplication independently of the first two. These things hang together. And they're not just syntax. Subtractable is not a concept. It's something you can say, but it doesn't make any sense except in the context of something that specifies, say, arithmetic. And we've always had concepts. Notice that C had concepts. Integral, arithmetic. They are just words in the standard, just like in C++, forward, iterator, and predicate are just words in the standard. We want to make them into something real, into code. And so basically, we're looking for something fundamental. Don't expect to find something fundamental every year. So I don't expect to once we've got a body of concepts to describe things, I don't expect to find one every year. It is not the minimal requirement for an implementation. If every algorithm is specified as a minimal requirements for its implementation, we have a problem. If we want to improve the implementation, we have to change the interface. That's brittle. What we need to do is to specify interfaces in terms of general concepts so that we can improve the implementations without affecting the users. And we also want to have so few concepts that we actually have a chance of remembering them. I could not remember that zoo of concepts in C++ OX. I do expect to be able to remember the concepts in C++ 14 or 17 or whatever, because there will be a few handfuls of them. Andrew Sutton and me worked on something, and we got the STL down to 16 concepts. I believe the current version is in that thing too. So what are they here? A concept is a predicate on one or more arguments. So basically, we say that T is supposed to be a sequence. Simply at compile time, we check whether T is a sequence. Somewhere there's a definition of what it means to be a sequence. Has a begin and an end, for instance, and we just asked if T meets that. If it's a sequence, answer is true. If it's not, answer is false. We can do that at compile time. We have const expr functions. We have functions that can be evaluated at compile time, and we can write things like that. This, by the way, describes running code. You can download a branch of GCC and try it today. This is not science fiction. A template declaration will look a bit like, you can write it out like this. Here we have find. Basically, we need a sequence S, and we need something where the value type of the sequence can be compared with equal to that of the other type T. And so it takes a sequence and it takes a value of that type. And now we can write code like that. It looks exactly as it used to. The only difference is we specified find precisely so that all the information for checking is available at the point here. So let's see what happens. Here we have a sortable concept somewhere, and it takes a container. We take one container, which is a vector, and one container, which is a list, and we sort the vector. Okay, the vector is sortable. Sortable asks for things like it has a random access iterator, which means that you can do subscripting on it and things like that. Everything's fine. Sort of a list will fail because lists are not actually sortable. They don't have the necessary stuff to poke in different parts of an object. The best way to sort a list tends to be to copy it into a vector sort and copy it back again. But that's beyond it's not done here. In the standard, this gives an error. And so here is the actual error message from this code. List of integer does not satisfy the constraint sortable. And if you hit, oh, thank you. And you can thank Andrew Sutton also. And Gabby does raise. By the way, if you hit another compiler option, it'll tell you why it's not sortable. It'll come back and tell you that it doesn't know where the square brackets are, the subscript operator. But I like the short version. Andrew likes the longer version. So that's a switch. The shorthand notation is, if you don't want to write all of this requires stuff, you can observe that you actually could write it. We need a sequence for which the value type of the sequence is equality comparable to the other template argument T. And then we can say iterator of T find. Some people like this notation, some people like the others. You'll have a choice. This is just a shorthand. It expands to the requires version. And we can handle essentially all of the Palo Alto technical report. Now, the Palo Alto technical report is 100 and some page document specifying every algorithm in the STL. And this was done by a group of about 20 people in Palo Alto 2 years ago. Sean was there, I was there, about 20. It was called by Andrew Lumsdaine from Indiana, who was one of the main workers on the C++ OX concept, and got Alex Stefanov, who's the father of the STL, to chair it. And we spent a week simply specifying everything. So first you figure out what you want, and then you figure out how you can design a language for doing it. That's the right way around. Don't go and look for fancy language features and see how you can use them. I mean, this idea that you look for problems that fit your tool is wrong. So we did it the other way around. All of the work on Concepts Lite is done from application and then back to how you can support it. And we don't have the semantic parts because, well, we consider that what would be much to handle just now. We don't see problems with checking templates in isolation, but we don't do it. That is, we check the use of a template. If a template is specified to require something, we assume that its implementation will stick to that contract. We don't actually verify it. We think it can be verified, but you have to be very careful. Those of you who have worked with strict functional languages like Haskell will know it's really hard to debug because you make some slight change to the implementation, like insert the equivalent of a printf, the interface change and everything has to change. That is painful. We didn't want to go that. We need more work, more experience before we standardize something like that, and we don't actually use the requires much. Overloading is fairly easy. We have two versions of find, one for sequences and one for associative containers. If I take a vector and a multiset, I try to find something in a vector. It will find the first overload and go and search along. For the second one, it'll notice it's an associative container. It'll pick the second one, and it will do the search in the associative container, which is certainly not a linear search through it. That works. And if you look at it, the overloading is based on predicates. And that means that we don't have a notion of a hierarchy or a refinement thing. We simply take the predicates, flatten them out as a Boolean expression, see which Boolean expression is a subset of the other. If it is, we have a refinement relation. If not, we just see what works. If it calls one function and not the other, it's fine. If it can call two, we pick the more specialized one. And if it can call two and they are not specializations of each other, it's an ambiguity error. That's the whole set of rules. It's just do a Venn diagram. That one, and that one. Finished. So we compute what the ambiguity resolution is supposed to be. And the classical example here, we take advance. Here is advance that takes an input iterator. Here's an advance that takes a bidirectional iterator. And here's the one that takes the random aliases iterator. They are implemented differently, and we are quite capable of picking the right one in all cases. Okay, how do we define it? Well, they're just Boolean expressions, so you write Boolean expressions. Boolean expressions get tedious, so you write functions that are return Booleans, and this all works in. To help you write, there's a requires expression that takes expression, and if it is a valid expression, it'll return true. If it's not, it returns false. This was supposed to be an implementation details, but everybody screamed they wanted it, so it's now part of the technical specification. And to recognize them syntactically, as I'll show you why we need to do that, we call them concepts rather than constexpr. But we simply take the word constexpr out and put concepts in, and so they're the same thing except for the syntax analyzer. So how do we get to sort of container? Basically, it's a terse notation is what I call it. It means sorting a container means sorting a type that meets the container requirements. And basically, that again means give me a type, check the container requirements on it, and use that type as an argument. So basically, these three are equivalent. I use the underscore to show that it's actually not it's a generated name that you can't actually refer to, but this is equivalent. So if you wanted to write it out in longhand yourself, you would write something like this. And it'll accept that's a container, and we can do this stuff. So this is part of this idea of making simple things simple. This is the simplest algorithms, work really nicely for this. They're short, and they look just like our traditional functions. So square root takes the square root of something that can behave like a double. That includes integers. Basically, you could think of the sort function as being, the square root function is being specified with a predicate that its argument has to be able to behave like a double. So we do the same thing in more general with sort. It requires something that can behave like a container. And we have this little predicate for testing it. Now we get back to where I want it to be. Here, sorts of doubles. This works, it doesn't. Sort of containers. This works and this doesn't. And we get the one-line error message there. So we can start thinking about generic functions exactly like other functions, and you know they look like other functions. Now, going from the simplest cases to the more complicated one, let's see that this actually, how we'll handle the complicated ones. Here is, here's merge. It's, yeah, it says merge right there. It's pretty ugly. It has given many people headaches, including me. And if you think that's too easy, try accumulate. It's even worse. So we need to get this stuff under control. And we looked at this. That's just too ugly. It's too easy to make mistakes. It's too repetitive. Not good enough. So let's try and simplify it a bit. We can say forward iterator. Forward iterator, we use the shorthand. And we use one requires, which is the predicate that takes these three and checks the connections between them. For complicated algorithms that take many arguments, very often you have predicates that takes all of these arguments and works some relation between them. As a matter of fact, I don't think you could have a good algorithm where there was no relationship at all. Well, that's at least rarer in this domain. And so this is quite readable, and we are trying to attack this problem. If that's your solution, we know what your problem is. You have to simplify. We can simplify even further. I just said we had a concept that tested that three types were mergeable. So we have a little notation using curlies that says, give me three types that meets this. And here are the way I'm using those three types. So we just wrap the whole thing up and saying, give me a set of types that meets my requirements. So that introduces three names in the scope for to and out, which we're using here. And it says that once you give me that in a call, I will execute the predicate mergeable on them to see whether it works. And that's the way it looks, obviously. We take three type names. The first one has to be a forward iterator. The second one has to be a forward iterator 2. Not necessarily the same forward iterator type. And then we have an output iterator, and we have some assignable requirements and a comparable assignments, and that's it. It's just a predicate. So this sounds very good. And we are, of course, not finished. That is, there are much more we can do to improve C++. So let me finish off by looking a bit on the challenges that's facing us, and they are many and complicated. Those of you who are into ancient Greek knows that this is one of the labors of Hercules. He's trying to kill the Hydra. very hard task. So C++ challenges. So we want to make a better language, and we also want to convince programmers that the new stuff is actually worthwhile. And that's relatively easy from actually getting people to use it in large code bases. But we first have to improve the language, then we have to convince people that it's worthwhile, and then we can start seeing the practical problems of introducing it in existing code bases that doesn't have it. I refer to that as source code rejuvenation, and that I think that's going to be an important issue. So basically, whatever we do to the language or whatever we do to the tool chains and implementations, we cannot eliminate C++'s major strength. That is, there's a lot of people who has a solution that ends up being worse than the problem for a large number of people. Compatibility is a feature in itself. That means that ugly things will not go away even when we provide good alternatives. We just have to get people to use the good alternatives where they can. So compatibility is necessary, performance uncompromising, portability where appropriate, and we would like to increase, not restrict, the application areas. If we could restrict the range of applications, we could get a much prettier language. But actually there's a quote by me from about '84 that even I can design a prettier language. That just wasn't the exercise. It was not the aim of it. It was to provide a more useful language for more people, for more application areas. And I think that is very well worth pursuing. So the challenges is we would like to close more type loopholes. We need to address concurrent programming. We need something that's higher level than the threads and locks style of programming, which is universal, necessary, and about the worst way of writing concurrent systems that I know of. We need to build libraries that provides higher level models. We want to simplify generic programming. I am looking at concepts. I mean, some of us have them today, but we should have them all next year. And we want to simplify programming using class hierarchies. I've been doing some work on multi-methods and functional style pattern matching. Some of it is available on my home pages, on the publications. The software is also available. But that's still research work, but I would hope some of it gets into the language. If not now, then later. You have to think in long term in this kind of stuff. Sometimes you have to sort of imagine what the world will be like in 10 years and then try and get there, as opposed to thinking, oh dear, it'll take more than a year, I can't do it. The next quarter is essential and all of that kind of stuff. We have to have some longer term thinking. Let's see. Better support for object-oriented generic programming. I'll get back to that, but I don't like the way the community sometimes falls into different and warring camps when they don't have any need to. We have to support combinations of our programming styles. We want to make exceptions usable for real-time projects. One of the things that I'm sad about is that exceptions are not used for hard real-time. It can be used for soft real-time. And the reason is very simple. We don't have tools that allows us to estimate how long it takes to recover from an error when an exception is thrown. The tools don't exist. I wanted to build them 5 years ago, and somehow I never got around to it. Being in a university, working with students, it becomes difficult to work on a problem just because it ought to be solved. It also has to be publishable, teachable, and fashionable. But we need to make exceptions more usable. And we have to deal with multiple address spaces eventually. The notion that everything works in a single address space is creaking. It's difficult. We get these big memories with lots of cores, lots of things, but they are not uniform anymore. Different memory takes different time to use and such. I think we need to think about that. We want many more domain-specific libraries, and we want to develop a better specification of C++. I think English text is maxing out in terms of what we can handle. So finally, I'll just do a little rant. I really dislike the word paradigm. It was invented by Kuhn and implies some superiority of one paradigm over another, and things change and everything changes and all the old stuff becomes bad. Christian Nygaard said, addition didn't actually become useless and such just because we invented multiplication. Nothing was overturned. You incorporate the old stuff. Maybe you have to rephrase the old stuff. Newtonian mechanics did not disappear just because of Einstein. It became a special case, actually a very useful special case. Similarly, I would like to see object-oriented programming, generic programming, and conventional programming just as different aspects that you can use in combination. And I want to be able to develop rules for how you do things that doesn't talk in terms of these paradigms, which may become semi-religions. And the focus has been on language features. Do I write templates or do I write virtual functions? And that's an incomplete synthesis. So I think it makes harm. It makes things complicated. It's bad code, and people write code, for instance, if they believe object-oriented is right, they'll write generic code using interfaces and virtual functions, which is less convenient than templates and run much slower. Similarly, you can have people who are so believing in generic programming that they make everything into statically resolved overloading, and they should have built a hierarchy and done a dynamic resolution. It will be much simpler and easier to debug and document. So here's an example of what I mean. I want to draw all elements in a container. And I want that container to have a value type, that is the type of the elements, to be pointers to shapes. Fine. And then I want to, for each element in the container, I want to call draw. Now, this is a generalization of the classical object-oriented programming, draw all shapes. That was first done way back in about 67 for use for a plotter. Before they had screens that could do these kind of things. So this is that old program. So it's obviously object-oriented code. Also, see here, there's clearly a hierarchy of shapes, and there's a virtual function that dispatches to the right kind of shape. This is object-oriented code. Obviously, it's generic. Look, it is parameterized on a kind of container, and you want to do the same, the element types to that, and then you call the for each algorithm. It's clearly generic programming. But it's also very ordinary programming. I just want to draw everything in a container, and I just call a couple of functions on them that happen to be a lambda, but hey, it's just a piece of code that's called. So I don't believe that you can credibly claim this one is one and not the other two. It's all three, and they integrate rather nicely, and we have to work on this integration. Okay, so we've reached the Q&A time, and I'm sure, do we have some microphones that people can use? Because I can barely see people in the back, and I certainly can't hear you up there. So, any questions? There's one up there.
Yes, on a mergeable concept slide, parameters were T1, T2, and T3, but in the body it might be referred as 4, 4, 2,
Can you?
You probably just found a bug. Which slide?
Slide where you defined the mergeable concept. I think it's 2 slides forward. Yes.
Yeah, it's an obvious bug.
Oh, okay.
The compiler would have caught it, but I still haven't figured out how to feed my slides into my compiler. Sorry, I'll fix it before we send out the slides.
Okay, this was too fast question. I will ask
Yeah.
one more and then I give the microphone back. So I was a little bit surprised that sortable concept seems to imply random access. Because you were saying that concepts are big things. And sortable is...
We have not gone through all the details and specified everything, but traditionally in C++, sortable had required random access. We also have a version where if it takes a list, it just figures it out. And I think the Palo Alto TR requires it to be random access. Maybe we didn't generalize enough. There's a round of further work that is a bit hard to do before the compiler is available, and the compiler hasn't been available for more than about 4 months.
Thank you.
So we'll take. So basically, we've gone over time, but we can take maybe one more question, just people can know. Tomorrow there's going to be an Ask Us Anything panel, so that's when you can ask questions for a full 75 minutes and whatnot. So for right now, we got one more question.
We have a
Yes?
problem then. I thought that one was counting down to my talk time as I... Well,
No worries. No worries.
Let's take a couple of questions.
You can take a couple of questions. All right. Because, I mean, basically, we're going to cut into a 30-minute break. We'll just make it a shorter break.
I will cut it into this. I'm
Bjarne-
up here.
the Bjarne break.
I have the microphone. I can cut into the break.
Hi. As I understand, all those new concept features, they continue like header-only programming, right? And how do you think it's gonna affect compilation time?
Okay. First of all, no, it's not header-only programming. The interfaces, of course, has to be specified in a header. We do hope eventually to get a separation, but compile time was something that worried us a lot. The runtime was all right for C++ OX concepts, no overhead, and they're all right for concept light, no overhead. At compile time, we are currently, with the first experimental compiler, running faster than workarounds. That is, if you compare a concept thing with an enable if thing, the concept thing runs consistently faster in the compiler. And this is before we do performance engineering on the compiler. Concepts light are designed so that we can take key concepts and make them intrinsics. So I would expect a production quality compiler to have things like regular and ordered as intrinsics, so that you didn't have to go to the header files. It is much simpler than what you're seeing today, and even with a first compiler, it runs faster, significantly faster than alternatives. And the overhead against no checking, I don't have a really good impact of that, but it's hardly anything. I've not noticed it, but I have measured it against enable if, and there we win. And the more complicated your header code gets in the workarounds, the relatively faster concept light becomes. Compile time efficiency was a concern, and we have met quite stringent targets.
One of the long-term things with C++ is string handling. String constants are usually constant, and yet the only way you can get it into any manageable form is typically to copy it into a basic string, and if it's occupies more than 15 bytes, you've got a heap allocation. and so forth. Yet, string constant is just an array of chars. It has a useless terminating 0 on the end. It decomposes to a pointer. Has anybody given any thought to actually building in better string handling, a more efficient string handling into the language?
There are certainly people who have talked about better string handling and for building it into the language. The problem is that there seems to be no general agreement about what is better. And until there is something that is genuinely better for all or almost all people, I don't think we will get an agreement to building something in. So it's something people talk about, but I have not seen anything really concrete in that direction. In particular, I have not seen the initial agreement about what would be better.
When I'm writing STL heavy code, I'm getting tired of writing all the begins, ends, and the iterator pairs. So you showed how to do it. Write a template for the container. What happens if you want to return a range of iterators? What are the tricks there?
Let's see. There are. That's what we're talking about. There's a range study group that's trying to work work in this domain, and I don't know what their answer is. I have used a variety of techniques, like a little type with 2 elements that keeps track of what comes out, but there's no standard yet. But there's people working on it. There is, I believe, a proposal. I haven't read the latest version. That's for 2 weeks from now, when we're meeting in Chicago to look over C++ 14.
One more question.
There's people agitating up there.
People agitating.
They haven't had a chance. Yeah.
You have a mic over there?
Yeah.
Okay, so in JavaScript we had the good parts that really made all the bad parts go away, and we use linter for that. Why not do something like that for C++ to give it a rebirth with all the new things you're adding?
That's my answer. It's not a subset of the language, but it's a presentation focused on C++ as it is today. And it's short. You can read it in a day. And then, of course, C++ will never be JavaScript, just like JavaScript will never be C++. Okay, I think it's break time. Thank you.
Thank you.